Hi, welcome back to three-phase AC circuits. Let us discuss before connection of star and delta connections concepts. Let us discuss in three-phase what is the definition of phase sequence. So, definition of phase sequence. So the phase sequence of a three-phase supply is the order in which the maximum values of the three-phase voltages occur. So in let us observe here, there can be possibilities of two sequence. Okay, one is RYB sequence and another one is RBY sequence. Okay, so if you take, suppose this is ER, EY and EB. Okay, let me denote this is one of the phase of the three phase ER, another phase as EY and another phase as EB. As we know, this is 120-degree displacement. So if you take anti-clockwise, so if we refer ER and the sequence is no reference is 0, ER is equal to so we can say now ER is equal to E at an angle 0. Okay, the next EY would be equal to E at an angle minus 120. We're writing it in the polar form. Then EB is equal to E at an angle minus 240. So this is the sequence for RYB. So next, if you take RBY, observe the sequence. This is RBY. So not normally, if you take the sequence now, the voltage, this is ER. Now after R, the B should come. B is lagging ER by 120 degree. This is EB and this is EY. Observe the equation now. ER is the reference again. It is E at an angle 0. EY is equal to E at an angle, sorry, EB is equal to E at an angle minus 120. Now EY is equal to E at an angle minus 240. So you can notice that if the phase sequence changes, so the phase shift between ER and EB is 120, but the phase shift between ER and EY is 240. So that is the interchanging of these two. Okay, with respect to RBY. Now, before proceeding with star and delta again, let us come up with another topic like we have what is balanced load. What is balanced load? So, a load again, if you have a three-phase supply, okay, if you observe this, if I have a three-phase supply, if this is the three-phase generator giving out a voltages, it has to be given to the load. So this is the load. So you can connect the load either in star or you can connect the load in delta. So we will be discussing the load connected in star and the load connected in delta, or the generator connected in star or in delta. Normally a supply system will always be connected in star form. Okay, so let us discuss now what is this balanced load. So if you take the load, if it is in star, so we represent the load in this star form. Okay, in other simple way, there are three phase. Okay, three phase, three loads. If you take, these are the three phase and loads. How do you connect? So the ends, let me call this as R1, R2 phase, and the ends of the phases, R phase as R1, and this as Y1, Y2, and this as B1, B2. In star, okay, in star, all the, if you observe this, all the ends are shorted here and all the leads are shorted here. Correct, one of the leads are shorted and this is taken out to the system. Correct. So that is, if you say this is R1, this is R2, this is Y1 and this is Y2, and this is B2 and this is B1. If you observe, see, this is R phase, B phase, and Y. The sequences are P5 here. Okay. So if you take that way, all the common ends, that is sequence, that is the suffix 2 is connected. So other one is given to the supply. So imbalanced connected, what we can say the definition as, when the impedances of all the three phases are exactly the same. That means Z1, Z2, Z3 are all same. We can write Z1 is equal to Z2 is equal to Z3. So when the impedances of all the three phases are exactly the same, okay, then it is said to be balanced. Okay. Otherwise, it is said to be unbalanced supply. If you say the voltages are also same in balanced load, okay, balanced supply or balanced load. So the voltages, the impedances and the phase shifts are same in case of balanced load. So in other sense, I can represent this for a balanced system. Okay. So simple vector diagram for a balanced system. So system can be a load or supply. So if you observe here, balanced system, all the three phases are having equal magnitude. Okay, you have Z1, Z2 impedance, Z3. So V1, V2 and V3. All the three phases voltages are same in magnitude and the impedances are same, and the phase shift is also 120 degree between any two phases. That is called balanced system. And what is unbalanced now? Unbalanced system, okay, or supply or load, unbalanced load. So observe this, I am representing this as, so now the phase shift between these three is not same. Okay. And if you say this is V1, V2 and V3, magnitude is not same because the voltage magnitude also changes, the phase angle also changes, and the impedance also changes sometimes. Then it is called unbalanced system. Okay. So now coming up with the next, that is the star connection. So to study the relation between, okay, to study the relation between, okay, line and phase, line and phase, okay, phase values. So phase values I'm talking with respect to current and voltage, okay, current and voltage. So when you take this is a star representation. Okay, so for better understanding, let us take a blank page to represent more clearly this one. So if you take the three phase, so let me rewrite this now, the same thing with the pen. So this is three phase star connection with the windings. Okay, balanced star connection. So this is connected to the line. So let me say this is supply and it is connected to the load. Okay. So load here. So this is now. So anything voltage between the lines. So this is called phase. Okay. Let me say this is called the phase. That is, this is called the phase. Okay. Between the winding, and this is called a line, between the line. Okay, it is connected to the line, that is the voltage supply line. Okay, that is what supply line you can take it as. So there is a difference. If you observe, the voltage across this is called the V phase, because normally voltage is measured between the two terminal. So this is called as V line. Okay, so in short, we represent this as VL and this as V phase. So remember, always the phase voltages is across the winding and the line voltage is across the line. So any two line, if you take, this will be the line voltage again and this would be the phase voltage again. Okay. So now representing this in a better way. So let me rewrite this again in a simpler way. Okay, to make understand with notations. So let us take an example now with all the three voltages and current together. Okay, let me take this as Y phase, R phase, YB, anti-clockwise. So the voltages, okay, let me take towards inside. This is neutral, okay, center. So we can write this as ERN and this one as EYN and this one as EBN, okay. And now the line voltage is, this is RY, so we can say VRY, okay. So this one also I can take in terms of V only, okay, instead of V. Voltage induced EMF is nothing but an voltage, so we can say VRN, VYN and VPN. So what is the line voltage now? This across this is between Y and B, so we can say VYB. And now this is between these two now. So we can write this as V RY, YB, and this can be BR, VBR. Okay, it's anti-clockwise. Like RYB, first you take the sequence as RY, YB, and BR. Okay, the cycle it has to be this way. So now to obtain the relationship between VRN and VRY. So we know VRN is your phase voltage and VRY is your line voltage, correct? So we need to find the relation between these two. Now for your understanding, if you observe in star connection, the line voltage, if I say the line current is coming here, so this is IR, the same current enters this node and it will flow in this winding, the same current flows here IR. Similarly, the line current IY enters here, this would be IY, and the line current this would be IB, which enters this winding is called IB. Correct. So if you observe in this, the line currents are same as phase current. So I can write the IR is your line current. Okay, I line. Okay, this also I line. So the I line is equal to I phase, correct, from star. If you look at it, as soon as this current comes here, it is flowing in the winding. So it is same as the line current in the phase. So this is anyway the same. Now we need to find the difference between these two, that is V phase and VL. So let us use the vector diagram to obtain the relationship between these two. So for that, let us write the vector diagram. Now we all normally take the reference as ER. So let us take a reference now. This is this is this is ER. Okay, to obtain one vector and proving the relation between these two. So ER, EY and EB. Now, if you look at this diagram, okay, you can refer this as ERY or ENR. Okay, anyway, it holds the same. So the line voltage, that is this ERY. Okay, this ERY is between this line and this line. So between this line, we have this voltage and this voltage. So what we can write now, ERY is equal to ERN plus ENY. I'm just interchanging ERN plus ENY. Correct. So if you observe here, it is this has to be changed as ENR. Yeah, ERN plus this should be for this. Let us take the other circuit which I have written. So for that, Let me redraw this. As previously I had written. So using this, so I had written the indication this one. So this is R and N. This is Y, P. So this can be VRN and this can be VYN and this can be VPN. Correct. So now if I want to write the vector diagram, now this is the line voltage, that is VRY. So VRY is the voltage. This plus this voltage is equal to this voltage. Correct. If you add these two. So let me add these two. This is VRN plus VYN, or no, sorry, this can be, if you take the addition in this way, that is plus V Rn plus Ny. Okay, Ny. Okay, but we need to get the suffix y as the first one, so we just interchange that with the sign negative, so Vyn. Okay, so ERN and V. You should get the suffix. See, up. So this is voltage measured from here to here. Correct. So from here to here, this should be VRN plus VNY. Correct. So this is the equation. But we need to get the suffix R and Y as the first suffix of V. So interchange this suffix Y and N. So we get VYN with the negative sign. So with that, now let us draw the vector diagram. See, I need to know VRY is equal to VRN plus VY. Now I need to draw the vector VRN minus of this VYN to get VRY. So for that, let us draw the vector now. So let me take vector here. Okay. So always we represent with this VR. So VR is nothing but V phase voltage. I am drawing the phase voltage. So this is another vector. So remember, this is all equal in magnitude because I'm talking about the balanced supply. Okay. So now I need, this is VR, this is VY and this is VB. Correct. So I need, now observe this equation. Vn is common in the both the sides. So if I want, I can just write Vrn minus Vi because neutral is anyway common here. So I need, Vr is positive according to this, but I need minus Vy. So take this vector in the opposite direction. Reverse this. This becomes minus Vy. Now take the vectors addition of these two and draw. This should be your VRY. Now we need to determine the angle now. So if you draw the, we know this, the sum of these is 120. So this should be 30. Then what about, sorry, 60. And what about this now? This should be 30 degree. Correct. So taking this now, let me draw the perpendicular for this line. Okay. And let me denote this as, the numbering as 0, C and A. So from this triangle, okay, triangle AOC is equal to 30 degree. Correct. AOC is equal to 30 degree. So now let me erase this part to write the further thing. So AOC is 30 degree. So let me continue the part now. So AOC is 30 degree. But now cos 30, if you look at that triangle, so cos 30 degree is equal to, if this is the 30 degree, I'm talking 30 degree. So cos 30 is nothing but OC by OA. The sides I'm talking here. So OC can be written as OB. So if I note this as B, so OC can be written at OB divided by 2 divided by OA. But we know OB is VRY, correct? OB is VRY. So we can write this as VRY by 2 divided by OA. Correct. But what is OA? What is OA? OA is nothing but V phase. Correct. VRY is nothing but line voltage. So now we can write cos 30, okay, is equal to VRY is V line divided by 2 divided by V phase. So further, so let me continue this equation here. Now what is cos 30? Root 3 by 2. Correct. So we can write this as root 3 by 2 into V phase is equal to VL by 2. So 2 get cancelled. So what we can write? VL is equal to root 3 times of V phase. That means the line voltage will be equal to root 3 times of phase voltages. Now, what is the power consumed by this three-phase circuit in star connection? So let us derive the power consumed here. So now, if I want to write what is power consumed in star connection, so power consumed P is equal to 3 times, because 3 lines we are talking, correct? RYB line. 3 times into power in each phase, correct? So one phase we have power. So 3 times of that will be in 3 phase. So this will be equal to 3 into, if you want to write in phase, E phase into I phase into cos phi, correct? P is equal to VI cos phi in terms of single phase, correct? In terms of single phase. Now three phase we are using this one. So that will be equal to that will be equal to 3 times of E phase can be written. V phase is equal to, what is V phase? V phase is equal to VL by root 3, because VL is equal to root 3 V phase. That is what we previously have derived. So V phase can be written as VL by root 3. And what is I phase? I phase is same as IL. Correct. So I phase, line current and phase currents are same in case of star. So into IL, okay, into cos phi. So this can be written as root 3 VL IL cos phi in terms of line voltages, because remember, we can measure the current and voltage in line only. We cannot measure it in the phase winding. So referring always to the line voltage and line current, we need to measure the power. So this is the power equation for star connection. So in the next class, we'll discuss about the delta connection of three-phase AC circuits. And thank you for watching this video.